Thank you everyone for coming. Welcome to B-Sides. Very excited to talk about our journey to secure home robotics at scale. I'll talk about a few things today. Basically, robotics platforms, what comprises of a robot, different components and sensors in a home consumer robotic space, some unique threats and attack surfaces for robotic systems. Then I'm going to talk about security and trust models for consumer robots, basically giving some analogies between your IoT devices, your other hardware devices, and how some of the attack surfaces are very different from the consumer devices that you are accustomed to. Then I'll spend some time talking about some of the security foundational work that we've done in the robotic space, and then basically talk about some trade-offs and challenges between security, privacy, and safety aspects. Some of the hard decisions that we have to make and every other company has to make when shipping a consumer device. And then lastly, I'm also going to cover some interesting privacy work that we've done as it pertains to robotics as well as consumer electronic devices. Quick introduction. I've been doing security work for 15 years. I started my career with NCR. Did a lot of payment security work on terminals and ATMs and check processing machines and point of sale machines, both hacking and securing them. Then I spent some time at Microsoft doing security engineering for Azure. Transitioned into a consulting role with PwC. Did a wide variety of security work all across US. Then joined a startup called Financial Force, and now I lead security and privacy engineering at Anki. For those that you don't know what Anki is, we are a startup based in San Francisco. We primarily focus on consumer robotics and artificial intelligence and machine learning, focused on vision and voice and other aspects that go into robots. About 200 people team. We've shipped about 1.5 million robots as of today. Some of the robots are in the toys and gaming and entertainment business. They were the best-selling toy on Amazon for the last 2 years. And then a lot of work that we have done, we've also open sourced, and a lot of developers and robotics professionals are basically using our tech to create more interesting robotics applications. Before I delve into the attack surfaces, I just want to get a brief overview of, there are different kinds of robots. There are industrial robots, consumer robots, big robots, small robots. Some are autonomous, some are semi-autonomous. Some have high degree of assurance, some have lower degree of assurance. But the way to think about, robots is that space is huge, and different types of robots have different security requirements, different threat vectors. Our focus today for this talk will be home and consumer robots. To give you a sense of where the robotics market is today, robots are everywhere. They're toys, they're companions for the elderly. They're applications for home assistance or healthcare assistance or companionship or manufacturing and industrial automation. And about there are some stats about how fast that market is growing. So basically, we want to be at the cutting edge in terms of be the thought leader on doing security and privacy work in the robotic space. What is the Anki robotics platform? Sorry. Yeah. The way to think about the entire stack is, a robot doesn't do much on its own. There are a lot of different components and services, both on device, off device, on the cloud, in the applications that comprise for a holistic solution. So we do a lot of the robotics functionality comes from the cloud, things like analytics, voice recognition. The robots that we just launched today, you can talk to it just like you can talk to Alexa and Google Home. So there's voice activity detection. There's some other interesting cloud functionality. From interface standpoint, this is how you interact with the robot. It has touch sensors. It can do perception, which basically means it scans through the environment it is in and makes decisions on what it sees and who he interacts with. we focus and invest a lot in the character and the emotional EQ aspect of it. And the reason for that is we want people to have a relationship with the robot. We want people to have, trust in their robots, and that also intersects with a lot of privacy and trust aspects that I'm going to talk about. Then moving forward from character, a lot of SLAM, which is the mapping and localization, and when the robot moves from point A to point B in your home, all the vision algorithms and all the interesting AI tech that we've developed. And then basically scaling that to more character movement and manufacturing and other aspects. So we also abstract a lot of this functionality in our SDK, not all different blocks, but for us, the security models are a little bit different when you think about how the robot behaves in your home versus how a robot can be programmed as a developer. And I'm going to talk about that as well. This is an example of one of our home robots. It has different sensors. It can see the environment. It can hear what you say. It can interact with people in your home. It has some brain of its own, which is some of it is local. A lot of AI algorithms that we've developed, and how the robot behaves and interacts is local on the robot, as well as some applications are pushed from the cloud. The way to think about the complexity is our robot comprises of, this robot has like 700 different parts. There are different sensors and there are different systems. There's microphone and there's camera and there's laser sensor and there's capacitive sensors and there's other wireless protocols that it enables and uses for communications. But in terms of complexity of the hardware, it's even if the size is small, the attack surface both inside and outside the robot is pretty complex. So I just want to give you guys an idea of when you start decoupling the attack surfaces, they're pretty different from your conventional applications. Talking a little bit about threat models, the way to think about this is if you are protecting your applications or cloud services, you mostly worry about application security, data protection, confidentiality, integrity, availability threats as it pertains to your product and service. When you have a physical product in your home and it can roam around and interact with people, then you have to worry about a lot of other aspects. Safety is a good example. If the robot fails, if it's bigger in size, if it's providing some utility, it can cause a safety risk. It can have some environmental impact. It can create hazards. There are costs associated with different applications and functionalities, and how do you think about optimizing those for a mass consumer electronic device? Trust is a huge aspect to us. Robotics, especially in the consumer space, is very, very new. Nobody knows what it would look like 5 years from now or 10 years from now. But if people don't trust that tech, IoT devices today are notorious for their bad security. We don't want our robots to be, treated that way. We want people to trust our robots. We want people to have an association with robots. We want people to have assurance of, if I'm buying a device, if the robot is supposed to behave in a certain way and provide a certain utility, I can have some assurance and trust on that's what it does, especially if it has, these sensors like cameras and microphones, and you buy and bring it in your home environment. So plenty of things that can go wrong. I just brought in some interesting examples of what has gone wrong, and just Google or YouTube for like robot failures, and you'll find like dozens of examples. Again, not all of them are security failures, but like I said, for security, safety, and trust perspective, there are a number of things that, you want to be able to basically give your customers assurance on. This basically is a funny example. If you go to the Department of Labor and just search for robot, like literally everything is like somebody died because of a robot. Understanding attack surfaces. So this basically, the way to think about the attack surfaces, let's say you have a physical device. Just consider all the different ways it can capture input. It's not just digital packets coming in and out through the internet. You have physical sensors, you have firmwares and OS and applications and the cloud and the robot interacts with all these different components. It receives different kinds of radio frequencies and signals, capacitive touch sensors, the world it sees through its camera, the vision aspect, the voice. So there are a lot of interesting attack surfaces using those sensors, and I'm going to talk in detail what those are. Some of the other aspects are also, if you think about what signals it receives, even the charging ports and the diagnostic ports are, big attack vectors. If you have ever done hardware hacking, you would know, things like JTAG and USB and all those ports that people leave open that you can use to basically either debug or hack a device. And then reverse the analogy to like what signals does the robot emit that you need to worry about. If the robot is providing some utility, in case of this robot, let's say if somebody just scans through outside your home, your environment of what kind of devices does this home has, and somebody sees, hey, here's a robot. It could be a BLE advertisement, it could be a Wi-Fi transmission, it could be some other sensor that beacons out that somebody can scan and basically look for interesting attack vectors. So there are interesting trade-offs between usability and security of what do you enable for how long. I'll give you an example. For example, when we do pairing of a smartphone with a robot, there's an BLE advertisement that goes out, but we only enable it if you physically interact with the robot. So it's not like beaconing out, hey, I'm a robot and I'm ready to pair all the time. So, hardware threat modeling, this goes back to, it's a little bit different from your software threat modeling that most people are used to in terms of how do you build attack trees and how do you do data flow diagrams. It's similar analogy, but if you start decomposing 700 parts and how does each part interact with a different part and what are your security boundaries and where do you start your root of trust and which sensor talks to what sensor and which bus is transmitting what kind of data. So we do a lot of hardware threat modeling down to the sensor level to figure out what are the failure scenarios, what happens if one sensor fails and the robot can't operate how it's supposed to operate, and then what kind of trigger or action we need to take. This is pretty interesting, but it also goes, very low level in terms of how you typically do threat modeling of any product. So I'm going to spend a little bit of time on the voice interface. So this is the problem with voice-enabled devices. If you look at the logical access controls and the digital realm of applications, people are conditioned to use, their authentication tokens or credentials of something that is tied to them. You go to a website, you enter your username and password. That's how you authenticate. You can have a two-factor auth. How do you authenticate over a voice interface? How do you treat with cases of like a mischievous neighbor who can also shout to your voice activated device the same way you can, or your curious child who may just send some commands. This is just a sample example of like somebody keeps ordering on Alexa and the parrot at your home learns how you order on Alexa and now it's basically talking to your Alexa device. So it's basically a very different model of authentication and interacting with the robot. So should you treat like voice interface as like an authentication signal? And the problem with that is, yes, you could add some step of authentication like, hey, if you're performing a sensitive transaction, I'll add a PIN. You could do biometric auth of like, hey, I can do voice recognition of this person versus that person. But then this goes to privacy and usability concerns around the more granular data you are collecting of your customers, the more creepy you become as an entity, the more risk you gather. For us, the decision we make is we don't want to collect data that is not used for any product. So yes, we could do biometric auth if we need to, but that's not a place we want to be, at least for now. There are other interesting attack vectors like, hey, what if somebody just recalls your voice and starts replaying? How does a robot detect, replay? Some more interesting hardware attack vectors are, when you have different sensors like gyroscope, your phone has a gyroscope as well, accelerometers and different hardware antennas. Gyroscopes are pretty sensitive if they have a really good antenna. You could basically measure acoustic signals, feed it into some advanced signal processing, and apply some machine learning, and you could actually identify speech. These are, still theoretical, academic, PhD attacks, but the more sophisticated the sensors become, the more plausible these attacks will be as well. Inaudible voice command injection, this is another interesting one where human ears hear a certain frequency of sound. The microphones can hear even what you don't hear. So what if you can create some voice signals which are ultrasonic, send it to the microphone treats it as a command and executes it. And these are pretty prevalent now. You can see people have started attacking Siri and Alexa devices and Google Home devices where you can craft these voice waves, send it to your device, and trigger a command. In the iPhone case, it's basically dial a number or send a text. And the more interesting research in this area is, when you start applying all these advanced neural nets and deep learning algorithms. This came out about a couple of years ago. It's called Lyrebird. Basically, it's a tech. You can give it like a minute of your voice, anybody's voice. Just grab a video file from YouTube, give it a 1 minute of audio. It runs its classifying and training algorithms, and then it can talk like you. It's not 100% accurate today, but it will give you a sense of how creepy this tech can become, especially if you're using these things for voice-activated biometric auth or like phone support. And if someone can speak just like you, how you speak in the same tone with the same linguistic manner, things start becoming really interesting. So the robot makes its decisions based on the world it sees, and its primary interface for that is the camera. We have developed a number of training models and classification algorithms that we feed to the robot, and we store them locally. And there are things like if the robot needs to go from point A to point B, how does it determine the best path when it's mapping the environment, where the objects are, where the collisions are, if it's a person, if it's an object. The problem with that is, the way AI today works is, you build a model, you have some algorithms, you run those classifications over some data, and you train it over the data, and you make trade-offs. The problem with making those trade-offs is, is this a chihuahua or a cookie or a muffin? If things start looking similar, you can start defeating the model classifications. You could add more, accurate sensors. You could combine other algorithms. You can start tweaking parameters, but these failure scenarios still exist. The best example I can give you is, in the autonomous car industry, this is a big problem where, yes, they have the same issues around mapping and, training their algorithms to recognize different stop signs. So once you train your model to recognize a stop sign, you're basically saying, hey, this is what a stop sign looks like. This is where the text will be. But if somebody puts some text above and below the line, now it's basically thinking it's a speed sign instead of a stop sign. And then basically your robot, whether it's a car or a physical robot or a home consumer robot, you are making decisions based on the world you see, and the world, the robot thinks it sees. There's a huge class of basically interesting research which is gaining huge attraction, which is called GANs. They are basically deep neural net classifications and architectures comprised of different neural networks basically attacking each other. This is another example of researchers fooling even the Google's vision tech to recognize something which technically is not. The adversarial examples are prevalent in deep learning systems. These algorithms are, a lot of them are open source, libraries from Google, training data all over the internet, and that's what a lot of people are starting to use without recognizing all the failure scenarios that come with them. Yeah, Ian Goodfellow, he has the Google Brain AI research. He has a number of interesting research papers on this topic for reference. So manufacturing, this again is a pretty interesting attack vector. If you think about the applications that, we are a 200 people company and we don't have our own factories and we don't manufacture our own devices. We partner with some of the leading companies in the world, who have all this tooling around scaling, a huge complex supply chain of, 700 parts and bringing them to a factory and manufacturing those devices, in a scalable manner. The problem with that is, if you're manufacturing in, hostile countries or, factories which you don't have much control over, there are a number of things in and out that ecosystem that, worry us. Counterfeiting is the biggest one. Your intellectual property gets stolen. People start manufacturing your clones. Then how do you deal with basically, and the more premium your product is, the bigger the problem becomes. Supply chain compromise goes from anywhere from ransomware hitting a factory to nation states putting, advanced malware in flash chips that you might bundle as storage capabilities in your robots. And there's no easy way to solve these problems, but because your robot is comprising from all these components taken from different supply chain sources, it becomes a big risk. Untrusted manufacturing lines, this is another interesting one. You have to basically trust the factory to perform some privileged operations. In our case, think about, they get very low-level diagnostic tools, which they can burn the secrets, they can test electronics, they can write firmware, and they can also disable or enable certain capabilities. And you have to basically give those people who, are building those devices for you, have access to these, privileged toolkits. End-of-life components is another interesting one. You have to make some decisions in terms of cost of what kind of, Wi-Fi chip or a BLE chip or a processor you want to use. But in terms of, consumer devices life, people use it anywhere from 5 years to 10 years till that stuff dies. But if those components are end of life, if those chips manufacturers are out of business, how do you patch or think about security of those components? It's a pretty complex problem and no easy way to solve it. And then gray market is, these are some examples of people basically putting up fake stores or basically taking stolen inventory or even downright copying our exact designs and creating things that look like us. We are small, we don't go after every single buddy, but as a company, it's of huge interest to us of how people are stealing or abusing our intellectual property. So I'm going to transition about some trust model considerations. These are some interesting problems, especially when you have a physical device and a robot. I give this analogy of if you had a web application or a mobile phone, you enter your credentials. That's how you authenticate the user. How do you authenticate a user to a robot? Especially if it doesn't have a screen and a keyboard. Do you enter credentials? Do you shout your password? Do you make it recognize you with some biometric fingerprint? And if you also have some logical access control outside the physical realm of the robot, let's say a web interface to control the robot, you have your username and password that controls the robot, but then the robot doesn't know that username and password, and how do you marry basically these two worlds? Especially if you start thinking about the developer ecosystem and the applications and the SDKs, things start becoming very interesting of what is an optimized trust model for a robot? Which users do you trust? The way we think about our robots are, these are family robots. You as an adult, you buy a robot, you bring it at your home, but your family and friends and everybody who's around it, the robot will interact with them. So how much do you trust them? They can give the robot some input. What kind of functionality should you enable for whom? Those are not easy problems. It's a matter of basically usability versus security versus privacy, and you have to optimize for that. then what kind of signals and anomalies should trigger, let's say, an adaptive auth. Let's say we detect something is not right, somebody is abusing the voice interface and basically sending ultrasonic waves that we don't recognize. Like, what should the robot do? Should it shut it down? Should it beacon a notification? Should it cry? Those are interesting decisions. Then this is another interesting one. Our robot is autonomous. We want it to be autonomous in the sense that it's basically on its own. It only basically responds to commands or actions. But then we also have this realm of people want to write apps, and there's an SDK. So how do you transition from an autonomous world to a semi-autonomous world or a developer world? And how does the security model change if somebody's actually controlling it through an app versus if it's autonomous on its own? And what is an autonomous behavior? It could be a signal on the robot, could be a signal in the cloud, could be a signal on a sensor. And those are not easy problems. Going to talk a little bit about, basically some aspects that I mentioned about how much do you trust and where does your trust start in the chain. We design our own electronics. We design our own hardware, but we don't make our own chips. We basically use commodity processors that the mobile industry has been using, but they have certain code running on their chipsets, and oftentimes it's kind of a black box, and I'll talk a little bit about what those things are too. Manufacturing facilities, primary users, secondary users, basically, you have to give them certain control on how they access and interact with the robot. So just talking a little bit about how we think or thought about securing our robots, basically we had some goals about, confidentiality, integrity, availability, cost, trust, safety, and those were like our high-level goals. And then we basically stepped down and derived security requirements, and a lot of controls that we designed are basically optimized for, the security goals that we have for our products. So high level, we basically start with, we want people to have assurance on what the robot does. So there are privacy indicators for different functionalities. If the robot is streaming to the cloud, if it's in listening mode, if it's taking a picture, the robot shows some clear markers like that green light that you see. There are different visual cues that will guarantee the user, hey, the robot is performing this action. Code authorization, this is something dear to my heart. What we want to do is, there's a huge complex stack of code that runs down from the hardware ROM to the bootloaders, to the operating system and the firmware and the applications that run on the robot. We sign and verify and check for integrity the entire file system. So we want to protect every code that runs on the robot, and every robot that we ship, we want to have assurance on if it's performing, if it's running, if it's operating. We can guarantee that, yes, it's our robot and it's running our code, and we signed it, and the robot basically verifies the boot chain and the code. So, in terms of code authorization, basically it starts literally from like when you power it on, the boot ROM basically verifies, the kernel, and the kernel verifies the file system, and basically the entire storage of the robot. So both confidentiality and integrity guarantees here. We also encrypt and sign our every single update. A little bit about hardware security. We, because of problems like counterfeiting, and we want to authenticate the robots talking to us, we basically generate crypto certificates and we burn them in the robot at factory time in a hardware key storage. It helps with many interesting cases like fraud and abuse and counterfeiting, etc. There's some tamper resistance IDs that we use for fingerprinting the device, and again, if they're not cloned or they're not the robots that we manufactured, etc. There's a hardware-backed key store, which is used for key derivation. So when we think about aspects like protecting data on the robot, whether it's photos or your Wi-Fi password or other data that the robot stores locally. We encrypt the hub, data partition, but basically the decision of keys are derived locally from the hardware key and the trust zone which is running on the robot. So we try to keep ourselves and our cloud and our control out of this key derivation mechanism. Gives better privacy guarantees, is a better security story as well. Then we have a huge hierarchy of keys for data protection, and then we also think a lot about how do we harden the hardware itself. So when we release our production robots, we disable all the privilege interfaces that commonly people use to attack hardware-based products like UART and JTAG and USBs and SPIs. The problem with these is this is often like a one-way street. If you disable them and you burn fuses in the SoC, there's no easy way to reverse them because, yes, you disabled all those things in production. So even we lose certain capabilities as a vendor. This is just a picture of like the trust zone that I talked about. In the hardware, there are capabilities around what we call trusted execution environment, similar to how some of the Android and the iOS phones do hardware-backed key storage and key derivation and privileged operations like password decryption, etc. So what about physical security? I mean, this is hard. You'll see people like you ship a product, people will take it apart. You'll have a blog on iFixit. They'll shame you in terms of, hey, they don't have any physical security. The problem is physical security is hard. There are different physical security requirements if the robot is performing your heart surgery versus if it's a toy robot. So it's a very hard trade-off to make, what's a good enough physical security? That question is not easy to answer. You have to balance between cost of a mass consumer electronic device versus, customer expectations versus serviceability. You could make a really secure hardware and add a ton of tamper resistance, but then you make, it harder for service and basically harder for, plugging in different parts. There are also challenges about, intellectual property protection. People hack your, devices and they want to get to all the interesting tech that you've built and burn on the robots. And then, like I mentioned, there are different requirements for if it's a consumer device versus if it's a commercial device. And, oftentimes the requirements derive, the capabilities of the robot derives what kind of physical security you want in the product. So another area which we did a lot of interesting work was around application and device pairing. And the issue there is, a lot of devices have these notions of pair it over Wi-Fi or pair it over BLE, and you pick up a smartphone and you enter your credentials and your application discovers the robot or the device that you have. And a lot of manufacturers rely on the Bluetooth. The problem with using like Bluetooth as itself is that whole space is broken. There are tons of vulnerabilities in the stack, in implementations, in the chipsets. So we designed our own crypto mechanisms and protocols on how do we do key exchange, how do we do authenticated encryption, how do we do bonding. Some of those bonding mechanisms require physical interaction that I spoke about. Like if you have to pair a new device, you have to go physically to the product, tap a button, only then it opens up its pairing mode. And it also pairs and makes, marries itself with the user who is the controller of the robot, and he authorizes, yes, I'm allowing a new device or not. On the OS and firmware security, I talked a little bit about the trusted execution environment. This basically is privileged code and operations which are executed inside a secure hardware processor, not in the user space land or the kernel space. remove and harden our operating system to basically remove all the debug interfaces like SSH and ADBD and fastboot, basically making attacking and debugging harder. We focus a lot on what are the unnecessary services that we have to remove and how do we reduce the attack surface. We also do some engineering on the OS and firmware side to basically run these applications and processes, especially the ones that talk to the internet or talking to a sensor, to run as least privilege and containerizing and isolating them for better security guarantees. Then limiting network exposure. Again, not advertise the services that are not needed. And we encrypt the data partition on the robot, so even if somebody steals your robot, you still can't get to a data without really going and breaking trust zone. And then file system integrity verification is just the way this works is you basically sign and verify every block of the storage, and even if somebody tampers one block, basically it fails. And then a lot of work on hardening of the actual operating system and the kernel, around stack canaries and basically recompiling your apps with certain flags which can harden the binaries for different kinds of exploits which are pretty prevalent. There are a number of challenges and trade-offs. For us, the biggest issue is, should we go and use a mainstream OS like Linux, which is well supported, or do we, for a high assurance robot, do you go and take a high assurance, more secure OS? The trade-offs you have to make is, if you go for a high assurance OS, there's not a ton of support in terms of the tooling and libraries and all the other applications you want to write. So you have to basically work with some commodity off-the-shelf operating system. I talked about the longer life cycle of consumer devices. You ship a consumer electronic device and a robot, people are going to use it for 10 years. Your clock is ticking. Windows XP was secure when it was launched, and look at where it is today. So how long do you patch your products? How do you patch things that you don't have control over, especially the end-of-life chips and the drivers and things that are outside your control? There are other interesting attacks on foundational platform security aspects. What happens if your processors or your platform has issues which are literally things like Spectre and Meltdown, or crack vulnerabilities in the Wi-Fi? Nothing you can control or do. It's basically some vulnerability in the protocol or some vulnerability in the hardware design itself. Those are pretty hard problems. And then the last one, which is people who spend their time in the Linux world or Android world or embedded security world, just tracking CVEs and known exploits in different Linux variants and kernels. It's just a huge nightmare. So cloud security, because the robot talks to the cloud, not only the robot authenticates the cloud, we also authenticate the robot back. It's a real robot, it's running trusted code, so we do mutual TLS for all of our services. We use modern, crypto algorithms. If you were using your laptop and a browser, you go to the internet, there's a key store in your browser, and your browser has a way to verify the SSL search chain. The way we think about the key store on our robot is it only trusts our cloud. So we basically remove pretty much all the major CAs and all the other certificates. So even if somebody hacks and even if somebody tries to man in the middle and put some certs and proxies, we basically want to make attackers' life harder. But the intent basically is the robot only trusts our cloud. It doesn't trust anybody on the internet. So authentication, code signing and stuff, from availability aspect, we think about which services are really critical. Secure update, token management, account service, authorization service, really thinking about how do we scale these for millions of robots all across the world in different geographies. Then a lot of tooling and capabilities we have to work on, basically detecting fraud and abuse. DDoS is just one example, but how do you detect anomalous behavior coming from robots, not users. We basically designed a lot of tooling for our own CA and PKI. There are some interesting challenges on the robotics side as well as embedded hardware. The first one is clock. To verify SSL and TLS certs, you need a good, reliable clock. If your phone's clock went back 2 years, suddenly everything will start failing. So if the robot doesn't have a clock and you power it on, how does it trust the validity of that cert? It's not an easy problem. So you can either rely on signature or you can rely on time. And we rely on signature, not time, because the device basically powers from the Unix epoch time of 1970. It has no idea of clock when it boots up. The second bullet talks about, what kind of capabilities should you build, when the home DNS is insecure, when the time service is insecure, they use UDP, the content delivery networks which are not in your control for like software distribution, and how do you think about securing those aspects? We use some interesting protocols which are newer, like gRPC. It does HTTP2. It can do both HTTP2 and HTTP1 in like single call, but then the tooling and capabilities of TLS libraries are not there yet. If anybody has ever managed and run HSM in the cloud, of how do you do key management distribution and the kind of limitations that HSMs give you from even the major cloud manufacturers, it's pretty amazing even in this day and age. And then the last one is a funny one, when you do all this work around confidentiality and cryptography and security, and guess what? You manufacture in China and the factory can't talk over those crypto channels back to you because something failed in the Great Firewall of China. So what kind of environment do you need to create in that other country to make your product work or test during manufacturing? Those are pretty interesting challenges. I'm going to talk a little bit about privacy. The hard privacy issues are, if you start thinking about this notion of, yes, enable the user, give them better privacy, it also enables a ton of abuse if you can't track where the traffic is coming from, which the user is, what kind of things he is up to. The second challenge is the way to think about managed versus unmanaged robot is, yes, if this was a commercial device and you were selling a service to a customer, let's say a robot projector, you want to build capabilities to manage those things remotely. So, device management and remote capabilities of you as a vendor, how much control should you have directly on the device versus the privacy aspect of once you have that control, then totally some three-letter agency can come to your door and say, hey, why don't you put a backdoor in it? Why don't you tell me data about this customer versus that customer? And we don't want to be in that space. So we have to make interesting decisions around, how do we enable, privacy for the customers. The third bullet about privacy is, for AI to be useful, you have to collect a lot of data. But the more data you collect, the more creepy you become. So how much data can you keep local? How much data do you stream up to the cloud? And how do you anonymize that? And how do you use that to basically train and make your products better? Those are also pretty hard decisions. The fourth bullet talks about, we have legitimate interest in providing customer support. People call us and say, hey, my robot is not behaving this way. I talked to it, I gave it these commands, and it's not working. So we need to give our own people capability to like, hey, if Talha calls, you should go and be able to look at the failure and tell the customer this is why it failed. But if you build that capability, then you also have insider threat of like somebody can abuse that thing. So those are like in very hard choices you have to make of what do we collect even for our own legitimate support scenarios. And then conflicting privacy requirements, we sell in Europe, we sell in America, if you've dealt with COPPA or GDPR, they have pretty conflicting requirements in terms of the right to be forgotten versus who can ask for deletion of data and who can provide parental consent. That's just a broken space. And the final bullet hits on, what data do we keep local versus what data do we keep on the cloud. What we do as a company, we took a decision, and we basically said we will not store any voice data in the cloud. All the commands that the user tells the robot, says to the robot, we basically take that voice stream, we understand what the user wants, we perform the action, and then we throw away the voice. We don't have any record of what anybody told or said our robots. And we do this deliberately, so it reduces our threat surface. It's also a better privacy story. If we get hacked, we don't have people's voices. We don't have anything to turn on to anybody. This is the privacy cues I was talking about. There's a very clear visual indicator and a privacy signal when the robot is listening and streaming up to the cloud. We do collect anonymized stats, which basically is how our customers are interacting with the robots, which aspects are more popular, and those are not tied to an individual user or robot. We are mostly basically, to improve our products, we're just curious about which functionality is more popular than the other, or which things fail that people want that we haven't built yet. Customers can always opt out, even of the anonymized user analytics. There are certain capabilities, and because we use cloud providers for various things, we only partner with entities that can comply with our legal and data retention requirements. This is a really interesting one, which again goes to this usability versus privacy aspect of the keyword and the detectivity signals that you give to the robot in terms of when you say, hey vector, do this. Those trainings and those classification algorithms, to make them more accurate, you need more data. We don't use our customers' data for training. We buy this data off the shelf, which is completely anonymized. But it does have some implications as well as impact on how accurate your voice capability is. But that's a decision we made as a company of we will not use our own customers' data for training our voice, because we throw away the voice data. And then we encrypt all data in transit as well as on the robot. And the vision stuff, for voice, we have to stream it to the cloud because the tech of doing AI locally on the robot is not there yet. But on the vision side, that thing has matured a lot. So all the training models and all the vision stuff that the robot does is all local on the robot. We don't stream images, we don't stream video to the cloud. And all the biometric data of even the people that it recognizes, those mathematical fingerprints, are basically stored anonymized locally on the robot. That is it. End user is in control. You can always just hard click, hard press the robot, and it will go back, reset to the factory state if you want to sell it off or return back to us. That's all. Here's my contact. Happy to, we have about 7 minutes, so happy to take any questions. Sir.
Boy, speedy. You mentioned there were challenges like, I think you called it the dolphin attack, where that seems like a very simple, low-tech way to get around something like that, is simply to put a bandpass filter that goes to only the human range of things, so nothing can go up to your cloud for analysis that isn't human voice, at least in that range.
Yeah, so we have capability to detect it because we write our own microphone firmwares. A lot of devices, they basically use off-the-shelf tech, which is already developed, and they don't have that level of granularity. So we can totally detect if it's not a voice frequency that looks like human or sounds like human. But even then, the early voice actor detection, that's local. So when you say a trigger word, and when the robot recognizes that trigger word, is only when it starts streaming to the cloud. So in the Alexa world, it's hey Alexa. In the Google world, it's hey Google. For us, it's hey Vector. So we only stream after we've recognized the trigger word. So we don't stream anything before that anyway.
Hey, great talk. Thanks.
Thank you.
So on your hardware security slide, you mentioned you had some cost constraints and you had to balance security versus cost in some cases. What are some of the things that you had to out of scope because of cost consideration? And rephrasing the question, if there was no cost constraints, what would you have done differently?
Yeah, great question. So I think the way to think about this is, so let's start with SoC, for example. Your mainstream processor is the similar processor that you use in your mobile smartphones. It's made by Qualcomm. It's a 64-bit processor with a CPU and a GPU and eMMC, and it has some interesting trust zone type capabilities. It's a smartphone. It's a processor from like 3 years ago, right? It's now way cheaper than when it launched. So the newer processors have more advanced capabilities, but then it drives up the price. For the functionality we have today, that processor is sufficient. That's like on one aspect. The second aspect is, BLE sensor. Would you buy a 5-cent BLE sensor or a 50-cent BLE sensor? When you know nothing about what is in that sensor, it's a black boxed firmware somebody wrote somewhere in Taiwan and China, and it's commoditized, which literally everybody else is using. So yes, if you had no constraints, you could design your own BLE sensor, you could write your own firmware, but that basically, raises the bar. There are tons of components that not just us, like everybody buys and uses, where, you kind of trust what comes from the supply chain. But then on the hardware side, again, I think because it's a toy, an entertainment toy, it has a plastic body. I mean, yeah, there's no films of tamper resistance and evidence. There are no seals. You can open it up and, put another camera next to our camera if you wanted to bug the device. But yeah, we could make it $100 more expensive and add layers of physical security. Even that is not perfect, but it raises the bar. So you kind of make these decisions for price point based on what the product needs to do and how premium it is. Any other questions?
Okay, big round of applause. Thank you very much.
Thank you.